Anyway, my name is Marshall Clow. I work at Qualcomm in San Diego. I also work on the standards committee. I tend to spend most of my time in the library working group. And I am the maintainer of libc++, the standard library implementation that ships as part of LLVM. So hopefully I know a little bit about this stuff. All the code that I'm going to show you compiled once before I stuck it on the slides and dinked with it to fit. So it may have some trivial, like missing semicolons or things like that. But it worked once. It worked once. So we're going to talk about customizing the standard containers. Now, before I start, I got to ask, how many people in this room saw Matt's talk Wednesday afternoon about that high-performance hash map that they did at Google? Right. OK. Setting expectations. This talk is nothing like that. Nothing like that. You know, he started with standard unordered set, and then took a sharp left and went out and did some really amazing things. But I'm going to start with standard unordered set, and I'm going to stay with standard unordered set. So, you know, I'm going to show you how to make it do things with your types, make it play well with your types, things like that. We're not going to invent a new hash table here. We're not going to invent a new kind of red-black tree or anything like that. We're going to use the standard containers. But hopefully I'll show you ways to do things that you weren't quite sure you knew how to do. OK. Also, if you have any questions, just raise your hand and ask, because don't save them up till the end, because chances are by then you'll have lost your train of thought, or I've lost my train of thought, and we won't get as good an answer. OK. Any questions before we begin? OK. Maybe if I turn this on, it'd be a good thing. OK, well, what are the standard containers? There they are. There are 17 of them, kind of. Well, 18 of them, kind of. Well, I say kind of because string is kind of a container and kind of not. And then there are the three container adapters, stack and queue and priority queue, which are not really containers. They add functionality on top of the other containers. OK. Disclaimer, that was not my stomach rumbling. My stomach rumbles, it's loud, but not that loud. By the way, as an aside, I'm a big fan of the container adapters, and it seems a shame that we don't have more of them. So, you know, if you have this idea for a container, you might think about, you know, can I do this as a container adapter? Reuse all the functionality in, say, deck or vector. I recently tried to write a circular buffer on top of a container and just decided the semantics just didn't quite match, but it was really tempting. I got really close. But anyway, these are the standard containers: array, vector, deck, list, forward list, set, multi-set, map, multi-map, unordered, unordered. And then string, because string behaves like a container, but it's not really. I think that most of the reasons that string is not classified with the rest of the containers is all the rest of the containers will take arbitrary user-defined types, while string takes character-like types. They don't have to be constructed, really. And the container adapters, like I said, sit on top of other things. OK. So we're going to talk about the ways each of these containers have customization points that let you, customization interfaces is probably a better way to say it, that let you bend the containers to your will, make it do what the designers weren't quite sure of or didn't know how to do for your types. In particular, there are three of them, and we're going to talk about these three today. We're going to talk about allocators, we're going to talk about comparators, and we're going to talk about hash functions or hashers. So just so you know, I'm probably going to call these comparison function and hash functions all through the talk. They don't have to be functions, OK? They can be objects. They can be lambdas. They can be std functions. They can be whatever. But I'm going to call them functions because it's a nice thing to hang on to. Anyway, there's a lot of power here. So we're going to start with allocators. OK? Allocators. Wow, it's Friday afternoon. We've had a lot of allocator talks this week. A lot of allocator talks. I just went through the schedule and searched for the word allocator in titles, and this is what, 1, 2, 3, 4, 5, and one of them is a two-parter. I am not going to spend a lot of time on nuts and bolts of writing your own allocators, because these people spend a whole hour doing that, and you can watch the videos. If I had been scheduled on Monday, I could say, hey, you guys should go watch these talks because they'll tell you how to make your own allocators. But it's Friday afternoon and these guys have all gone already. They're done. They've given their talks. And so you're going to have to watch it on YouTube or Channel 9 or wherever. But anyway, Bob's talk yesterday was really good. I didn't go see John's because I've seen John's before. And Alistair's I didn't see. Alistair and I have talked about this. And then Pablo's stuff I have also seen before, so I wasn't in his talk this morning. But anyway, there's lots of stuff here. And since the Bash Films people are so good at getting the videos up quickly, you should be able to not wait forever to do this. Okay, so how does this actually work? This is a declaration for vector, a forward declaration for vector, taken right out of the standard document. Okay, except I added the std part here. It doesn't actually say that in the standard. But vector takes, you think of when you write a vector, you write vector bracket int. Okay, and you go and use it, and that's fine. But really, vector has two template parameters. And the second one is your allocator. And it defaults to std allocator of int. And the allocator is typed just the same as the value type of the container. And in fact, if you try to pass my allocator of string, it'll fail to compile. So that's all well and good. But anyway, but what does a vector do? Okay. Sorry, a note here. In these slides, we have two things here. We have the type of the allocator, right? Which is all well and good. You need to get the types of everything right. But when you actually make a container, you need not a type of an allocator, but an actual allocator object. Okay? And in a lot of the examples that you'll see around the wide world of the internet, they just talk about this, and they don't ever say anything. But there needs to be a way to go from this type to an object. How do we do that? It's called a constructor. So sometimes when you create a vector, if you just say vector int like this, if you say vector int std allocator int v semicolon, the vector gets default constructed. The vector contains an allocator object inside of it, and that allocator gets default constructed. But you can create your own allocator and pass it to the constructor of vector, and it will use that. Or you can provide parameters to the constructor of vector to initialize your allocator. You want to be really clear about the difference between specifying a type here and specifying an allocator instance in your containers. Most of the time your allocators will be default constructed because that's what people are used to, but they don't have to be. Anyway, so we want to keep the distinction between the type and the actual instance clear. And that will be true actually for the comparators and the hashers too. Okay. So what can I do with that stuff? What does an allocator do, I should say? What does an allocator do? Really, okay, there are 4 things an allocator does, basically, that are really important for you. And 2 of them are optional. The first ones are, it allocates and deallocates memory. And traditionally, this is all an allocator did, okay, back in the C++ 2003 timeframe. But that's what an allocator is all about, right? It comes from the name, allocator. It allocates memory, and it deallocates memory. But In C++ 11, 14, I don't remember which, we also added the capability to construct and destroy objects. Now notice, when you create an object on the heap and you say new int blah, right? You get back a pointer to a bunch of storage that has an already constructed int, or new foo blah, that has a constructed foo in it. You get a pointer to an object, and the object is ready to go. Okay, there are two things going on there, right? The first one is some space is allocated, and the second one is that the object is constructed. In the allocator interface, those two things are split apart. You allocate memory, and you construct an object. And those are two separate calls to the allocator. And on the way out, the inverse thing is the same thing, but in reverse. The object is destroyed, and then the memory is freed. So you have allocate, deallocate, and construct and destroy. And construct and destroy are optional. You don't have to do those in your allocator. If you don't do them, there's a bunch of plumbing in the standard library which will give them default implementations, which are just like calls to placement new and calls, and a call to the destructor. So if you don't have any special requirements on object construction and destruction, then you don't have to actually do any of this stuff. Okay, so what do they look like? What do these things look like? And these, I give you sample implementations, or simple implementations is probably a better way to say it. So allocate takes a size and returns a pointer. And since allocate of t, this is an allocator for objects of type t, it returns enough space for n objects of type t. Okay? Deallocate is given a pointer and a size. This is the size deallocation stuff that was added in C++ 14, but you don't have to use that. And here we just call operator delete on p. Now, what's going on here with this funny cast to void is we're saying basically we're not running any destructors here. Yes, Gaspar.
Is size guaranteed to be positive, or can it be 0?
Size? Which size?
The n.
N? It's a size t. It's an unsigned number.
So, I mean, does it have a precondition or not?
Oh, I see what you're saying. Can you pass in 0 to it? Wow, that's a good question.
Is it UB, or are you required to handle it?
I don't know. My belief is that it has to be big. It has to be at least big enough for 1, but I don't know that for sure. I'd have to look it up. So the question was, what are the preconditions on the value of n that is passed to allocate? Can it be 0? Obviously it can't be negative because size t is an unsigned type, but can it be 0? Can you allocate nothing? And I don't know the answer to that. I mean, it's not a sensible thing to do, but that's never stopped anybody in the past.
It is a sensible thing to do.
Well,
yes?
Well, I was saying it might be undefined behavior.
Yes, it might be undefined behavior. I don't know. I suspect that I could research it and tell you, but I don't know.
You can do that for malloc, and it will give you a unique pointer.
Right. Malloc has defined semantics for size of 0. I do not know if allocate does. So, but yes, malloc will in fact give you that stuff. But malloc does that as far as I know. That behavior was put into malloc because they have realloc, and you can resize something later. Because really, a pointer to a block of 0 bytes is not useful. If you can resize it to something useful, then yes. But C++ doesn't have the idea of resizing a block of memory. We just allocate a new block, copy the useful stuff over, throw away the old block.
Yeah.
What? That's as may be. Thank you, Vile. Anyway, one of the things you can depend on is that your deallocate function only gets handed pointers that came out of your allocate function. You don't have to handle other people's allocations, okay? You don't have to handle just some arbitrary pointer. It has to be a pointer that came out of your allocate function. So for example, if you're allocating out of a pool of memory, right, and you're handing out pointers into a pool of memory, you're not, unless there's a bug somewhere, right? Bugs always happen, but in general, you can assume that when you get a pointer to deallocate, that it's something in that pool, and in particular, it's the start of a heap block that you allocated with alloc. You don't have to protect yourself against something really malicious. Yes?
I think I know the answer, but the container is going to call my allocator both for the data that I really want, i.e. the string, as well as, say, the string class members it needs to manage the container.
So the question was, is the container going to call the allocator to handle both the data for, say, a string, the actual character data for the string, as well as the string class members to manage that? And the answer to that is, it depends. In the case of string, the answer is actually no. The allocator is only used to allocate the character data because all the other things are member variables in the string object. But when we get to the node-based containers like, say, list, it calls the allocate to allocate what is called nodes, and the nodes contain a T and 2 pointers, a front pointer and a back pointer.
That was the question I was going to ask.
Okay.
So, yes.
Somebody else have a question over here?
Yeah, how does this work with deep propagation of allocators? Not sideways like for list nodes, but if you instantiate the vector of string with allocator,
Mm-hmm.
and your allocation resources are MROs,
Okay.
then your vector has to propagate the allocator to the inner strings, right?
That's something that's actually new in but basically so the question was, suppose you wanted to say a vector of strings and you wanted to make sure that all the vector stuff was in a memory resource, and then all the string data was in the memory resource as well. And what you would do is Arthur here? Arthur gave a class before the conference about, the standard library from scratch. He spent 2 days going over a whole bunch of the standard library. But anyway, what you would want to do is you want to say the strings that go in here take an allocator which allocates out of the same memory pool. You give it a PMR and a polymorphic memory resource as the type, and as the instance you hand it one that says, here, I want this to go into this pool. I saw a hand coming up over here. No? All right. Yep.
Yeah, I just was wondering, this might be killing yourself, or shooting yourself in the foot, but could you actually say that you might have a allocator which is a global allocator, and you want to keep all track of objects that kind of use the allocator, and just you want to make sure that when you delete something that it's actually owning to the object that you deleted. Is there any way you can kind of customize these functions to say that instead of just passing in the size t, then you also pass in the size t and the caller, or is that?
That's okay. So there's a bunch there. Okay, the original wish that he wanted was to have a global allocator that in fact logged all allocations and deallocations and track their owners. And that's certainly possible to do. There's 2 ways to do that, by the way. One is you can do it via an allocator, but an allocator is per container. That's not all allocations, but that's all allocations for a container. And so if somebody just calls, says new foo, that's not going to track it because that's not in a container. But you also have the opportunity to replace the global operator new, which will do that for you, new and delete. Those are replaceable functions. That's a little out of the scope of that talk, but it touches on this stuff. But the second part of that was determining who the owner is and keeping track of that. And that's, you're not going to get extra parameters to operator new and delete or allocate and deallocate, because the things that are passed to it are usually passed, well, in the case of the allocator, they're passed by the containers. And They know to pass one parameter. You could, in fact, if you had, whose was it yesterday or this morning about stack tracing thing? If you had a stack trace utility, you could look down the stack in your allocate and figure out where it's being called from, but I'm not sure that may be more work than you want to do. Anyway, so big thing here is, yeah, separation of concern, allocation versus construction. Okay, so what can you do with this? Well, there's lots of things. One of my, we talked about this. Actually, I'm sorry, it's coming up. But you can manage your own memory pool. People in the embedded world, okay, say, we can't have any dynamic allocation in our program because we're an embedded machine. And I've talked to several of them, and I say, really? How do you handle such and such? Or how do you handle such and such? And they say, oh, I allocate a block of memory at system startup time, and then as needed, I handle pieces of that out. And I say, that's dynamic allocation. You're just not doing it in the global heap. Okay? You can make an allocator that runs out of a little memory pool, and then you can use vector or map or set or deck or whatever, and it will stay in that little memory pool, which satisfies the people, no dynamic allocation. I mean, no dynamic allocation of the global heap, but that's fine. You can allocate in shared memory. If you have a shared memory area that's shared between different processes, you can teach an allocator how to put it out there, and you can have data structures that are shared at memory speeds between different processes. Now you have to play some games with pointers to make sure that if you have something like a list, that the pointers are relative to the start of the shared memory block, but that's like so that you can traverse the list in both address spaces. But
how about relative to their own list pointer?
That's another way to do it. The comment was relative to their own list this pointer. That's another way to do it. But there is there's a facility in the allocators, which I'm not really going to talk about other than mention it, which we call fancy pointers or non-native pointers. And basically, these are things that look like that represent memory addresses, and you can turn them into actual real memory addresses through a call, but they don't have to be raw memory addresses. You can allocate. You can enforce alignment, which is really nice because maybe your underlying implementation of malloc doesn't actually have the alignment guarantees you want. So let's say your underlying memory allocation gives you 4-byte alignment and you need 8. Well, you allocate an extra 4 bytes and then optionally bump your starting pointer by 4 bytes, and you get 8 bytes alignment. You can you can hand stuff out of a memory pool. John Lakos did 2 hours about arena allocators, where you just, you put them out of a pool. Many years ago, I wrote a spam filter for an email program I was working on at the time, Eudora. This is what I did when I started working at Qualcomm, back before free email clients killed paid email clients. But I wrote a spam filter, and one of the data structures I had was a map of strings to integers, where you look at individual strings, tokens, whatever, and you got a score, and then you do a bunch of Bayesian calculations on it, and you come up with all the words in the message, and you come up with a score which suggested how spammy this was. Well, this was a big data structure. And actually, we had two of these data structures. We had a fixed one, which we shipped, and then a much smaller one, which the user could train to their particular thing. They could say, yes, this is spam, or no, this isn't spam, and it would learn. But the fact that the big one, the fixed one, never changed, I thought to myself, I don't really need those strings. I don't need all the power of strings. I just need just the raw text. And so I changed the It changed the map from a map of int comma string to a map of int comma char star. And then when I read the data in, I just allocated a big block of memory. I think it was like 64K. And I laid the strings into it one at a time, the character data, and pointed it in there, slapped a null on the end. And if I didn't have enough room, I just went and added, allocated another 64K, because this data never changed. I never had to delete it, right? When the program was over, I just let the whole block go because it didn't matter. It never changed, and the program was ending. And you can do the same kind of things with memory pools. If you know that something, you know something about your memory usage, about your the way your objects get created or destroyed, you can take advantage of that. This is a very general solution, right? And the heap manager in your OS, whether that be jmalloc or tcmalloc or whatever, is a very general solution to that. Maybe you have a situation like I did where there's no deletions or almost no deletions, and that it's if you have, say, 2 million spam words, and over a course of a program run you delete 2 of them, you know what? Just let go of the pointer and let them go. You've wasted 30 bytes of storage. Big deal. You'll save way more than that in code space trying to manage a free list. Anyway, this is a place. The customization point here is for you have special requirements. You know more about your system than the people who designed this very general mechanism. That's when you want to customize. Okay? Okay, talked about that. These are the optional calls: construct and destroy. This is a very simple implementation, and this is the implementation you will get if you do not, in fact, implement construct and destroy. This is the implementation that the standard library will gin up for you. You say template class that says I need one of these, and these are the arguments, and put it here. This is a pointer you got back from allocate, or some function of a pointer you got back from allocate. Because vector, for example, will allocate enough space for, say, 20 of these, and then call construct throughout that block. Anyway, so it calls placement new, and then forwards the args, and you're done. And destroy is even easier. It just says, you destroy yourself. Call the destructor. Any questions about this? So the question is, what would be a typical use case when I would want to specialize this? I'm glad you asked that. See me afterwards. I'll pay what you wanted. Okay. Suppose you wanted to, thank you, register every object creation and every object destruction, log it, something like that. This is a great place to do that. Suppose you wanted to add parameters to your constructor call. I mean, you can do that. You can, just because you get these args to pass the constructor doesn't mean you can't swizzle them around or add some or leave some out or whatever. You have a lot of freedom here. You can give each object a unique ID or a unique tag. It's not serializing them, but I don't even want to say memoizing, because it's not those. It's marking them, stamping them, each unique one. This is a great place if you have to do a global registry, if you have to do a registry of some kind, right? This is a great place to do this. What people like to do is they do this in the destructor. They do it in their destructor. They have this global registry of objects, and in their constructor they register it, and in their destructor they deregister it. Deregister, is that even a word? Anyway, the problem with that is that it's undefined behavior. If you have to actually look at, if the process of deregistering it has to look at the object, it's undefined behavior. Because, why? Because once you enter the destructor, the object of the lifetime has ended, and none of the invariants can be guaranteed anymore. And so if you have, say, a map of things, and in your destructor you call remove on the map, say find this object in the map and remove it, or a set, say, you don't really have the guarantee that it'll find it in the set because you're trying to find this object whose lifetime has ended. Now, if you're just a single class, right, no inheritance or something like that, it probably is going to work, but I'd hate to depend on it. If you're going down an inheritance hierarchy, your superclass's destructors have already run. Yes?
I'm curious, because it returns void and construct one. Does that mean that this is the place where I assert that the pointer is suitably aligned? Because I'm not allowed to actually change it then.
You're not allowed to actually change it, no. You could have...
New returns the new pointer.
Right, but I mean, you already have the pointer.
Well, yes, but I thought that placement new was allowed to adjust for alignment and then return the pointer, and then std_launder comes and screws with you and all that stuff.
That has changed a lot in C++17, okay? Yeah, the whole extended alignment stuff went into 17, and we're still figuring out exactly all the places that needs to go.
Okay, so, but my actual question was, if I have data that needs to be 265 to 56 byte aligned, is this where I assert for that?
No, I would assert,
Well, but if I allocate, like, let's say the size of my datum is actually, I don't know, 10 bytes. But
Yeah.
it needs to be aligned to that value. And that requests I need, this many of these. So the vector is going to try, like, size of t, okay,
right,
next
times
size of t,
Right.
and that's when I want to assert. Like, you're trying to create something in a place that isn't actually good.
No, there's some funny stuff going on here that I haven't shown, and I'm trying to remember exactly where it comes in. Because if you try that with vector, you get the same layout as an array of those t's, and then every element will be 256 bytes long.
Because that's the align of.
Because that's a line of. But before C++17, the extended alignment, the stuff bigger than long double, you had no guarantees about it, either in array or in vector or anything. And in particular, in vector, you didn't get it. So don't know. Don't know where that kicks in. Yes?
Because the allocate here, you study cast the P to be Y pointer. It's try to prevent the destructor to be called.
Yeah, because we have destroy, which calls the destructor. Again, we're separating the concerns. We're separating the destruction of the object from the freeing of the memory. Yes, you are exactly right. The question was, is the reason here that we are static casting this to void before calling delete, is that to prevent the destructor being run? And yes, it is, because we run the destructor somewhere else. If we just passed a T star to, if we said delete P, it would run the destructor. Okay, so what can you do with this? Like I said, you can log every object creation and destruction. You can inject additional data, all sorts of things you can do. Okay, some really simple examples about using your own allocator. Okay, I have my own allocator here. It's called alloc. Okay, I'm not showing you a definition for alloc. I mean, please go to some of the other talks to see really how to write your own allocators. But we're going to assume that alloc has a default constructor and has a constructor that takes 3 ints. Okay? So we have vector int v1. This uses std allocator int in particular. We have vector int of alloc of int, v2. Okay, v2, when v2's constructor gets run, it's going to default construct an object of type alloc int. Okay, just like the first line, when its constructor runs, is going to default construct an object of type stdallocator int. Okay, now here I'm making a type def for my vector. My vector v3, this is very much the same as v2. My vector v4, I'm passing in an allocator. I'm making an allocator and passing it in, and that's going to get, because it's temporary, it's going to get moved into the vector. This bottom one down here I'm declaring an allocator of int, and then I am making another vector, v5, and passing in the allocator as a constructor parameter, and that's going to get copied in because it's not a temporary. So the point, the reason I made this slide was to drive home the fact that the thing that I talked about earlier is you want to keep the type and the instance of the allocator and the comparators and the hash functions. Make sure you're clear on the fact that they're two separate things. Most of the time, people will do things like this, where the allocator gets default constructed. And in almost every sample program you ever see, the allocator will never get mentioned. It just gets default constructed, and everything happens behind the scenes. But you can create your own allocators. They're variables just like everything else. You can pass them in. They have to get copied between containers when containers get copied and things like that. There's a whole infrastructure there that I'm not going into. But the point is again, keep track, make sure you know the difference, or actually, you guys all know the difference. Make sure you're aware of the difference between the type of the allocator and the actual allocator variable. The allocator variable is stored as a member in the vector. Okay, any questions about allocators? Yes?
So, given all that, how would you implement, back to the spam filter, how would you implement something that
Whoops.
can allocate lots of strings or lots of memory, but then delete it at once, get rid of it at once? Do you just not call delete in your program?
Well, okay, so there's a couple ways to do it. The question was, going back to the spam filter example, how could you write something that where you could allocate a bunch of things and then delete them all at once, or not delete them at all? So what I did was I made my map be a const char star int, mapping of a word, which is a null terminated string, a null terminated C string, to an int. Well, pointers like that, char pointers, they don't have destructors. You know, when the map gets torn down, the character data just leaks, which was fine because the map got torn down at the end of the program when I didn't care. You know, all the nodes in the map got deleted, but the actual character data didn't. But then I had these blocks containing those, and they just, you know, at the end of the program, the environment got torn down, they went away. But you could, in fact, you know, you could do things like, you can play games here to not delete things. You can manage you could keep a cache here of, you know, the last 4 deletions and reuse them. You can do all sorts of things here.
So if I don't delete here, then how do I delete at the end of, like, for the whole block? You could. I just do bookkeeping.
Yeah, you just do bookkeeping. The question is, if I don't delete here, how do you delete it the whole block? You can delete the block, say, when the container goes away. Say. You know, you can coordinate between the container and the allocator. Or actually, a better place to do is you delete the whole block when the allocator gets destroyed, right? And then you just, what John Lakos likes to call winking out. You just, it's all gone. You don't run any destructors or nothing. Yes?
Could you actually have the deallocate just do nothing rather than just do a delete operator?
So the question is, can you have your allocator just do nothing instead of actually call delete? Yes, you can. It means the memory usage of your program is only going to grow, but, you know, presumably you have a good reason for that.
Well, I was saying if you're basically not really allocating space or anything, maybe you're using a
Mm-hmm. Yes.
That might be a reason why you want to do nothing.
Absolutely. If you're allocating out of a buffer that you're planning on deallocating all at once, which is what he was asking about, yeah, you may want to, when the time comes to deallocate an individual element out of there, you just say, no, I'm not going to do that. That's fine. As long as either they're simple types or they get destructed or you don't care about the resources they hold, you're fine.
Well, I think the destructive might be better.
Call the destructor without chance to delete.
Yes, and that's the whole point of having both deallocate and destroy is one runs the destructor, one frees up memory. Okay, so I was going to spend about 20 minutes on allocators, and we're 45 minutes in, so I'm going to move along. Anyway, so let's look through the containers, right? So let's start with array. Array is the simplest thing. How does array use an allocator? It doesn't. It doesn't at all. Array stores all its elements on the stack, just like a built-in array. It doesn't have an allocator parameter. It's done. Okay. There are contiguous containers, vector dec, and string. They allocate in chunks. Vector puts all the stuff in one big chunk. Dec has a lot of blocks. Each holds several elements. String may not use its allocator at all. Starting with C++ 14, 11, you can have a small string optimization where it stores the string data in the string object itself, in which case it never calls the allocator. Okay, list and forward list are node-based containers, which means that they will allocate nodes that contain a T and some other stuff, usually for forward list, it's going to be a next pointer. For list, it's going to be a next pointer and a previous pointer. The associative containers are node-based containers as well, as are the unordered associated containers. They allocate nodes rather than just T's. So that's how they that's how they use their allocators. Okay. Associative containers. I'm done with allocators. If you have questions about allocators, I'm happy to answer them after we're done. Okay, associative containers. Here's the definitions for set and map, and the same definitions for multiset and multimap are the same, except for the name. Okay, we have a key, we have an allocator, which is an allocator of key. That looks very much like vector, and it should. But there's this thing in the middle called comp, and that's new. And for map, we have key and T, key and value, and alloc, and then comp. What the heck is comp? Comp, because the associative containers keeps things in an ordered tree, they need to know how to order them. Okay? They need to know how to order them. And given an arbitrary type, how do you order an arbitrary type? Here's an example. Here's an example of a comparison function, okay? This is not a function, right? This is an object that has a procedure call operator, member function, but I'm going to call it functions. This can be a lambda. This can be a functor. This could be a std function. This can be a pointer to function. This could be one of these objects, right? Doesn't matter. The point is, can they be called with like they were a function, right? That's kind of the definition of a functor. It's something that can be called with procedure call syntax. Okay, so a couple things to note. It's a const member function, okay? In C++ 17, this is required. Before C++ 17, it's merely a really good idea. Okay, and I'll tell you why. Suppose you have a set, and you have a comparison function like this, and you forget to make it const. And you try it, and it works just fine. And you're going along, and you're putting things in your set, and everything. You run your unit tests, and everything is great. And then you add a new procedure in your program, and you call it, and it takes your set by const reference. And suddenly, it fails to compile. And you get spew all through your console, and you look through it, and you look through it, and you look through it, and it comes down to, it says, attempting to call a non-const function on a const object. Okay, when the set is const, the comparator, which is a member variable of the set, is now const because the whole set is const. And if you have a non-const member function, it will fail to compile. You can't even do things like find in a set that's const if you don't have a const comparator. libc++, tooting my own horn just a little bit, will static assert on this and give you a really nice error message. It says, no, your comparator has to be const. Anyway, other things about this. This is a really, really terrible comparison function. This is a terrible comparison function. Compares the last names. It sorts by last name, right? You put this in a set, what does this mean? It means that Bob Wright and Ted Wright, you can't put both of them in the set because they have the same last name. Because it will say, oh, they're the same. How many people have heard the term strict weak ordering before? How many people want me to not rant about strict weak ordering for a few minutes? Yeah, Ansel. Ansel, do you have a question or do you want me to not rant?
This is a really bad comparison function. It always returns false.
Yes, even better. That's an even better. Thank you. It should say yes. As Ansel said, it always returns false. This should be L, left-hand side, not right-hand side, right-hand side.
That's why you named them X and Y.
No, that's why I named them left-hand side and right-hand side, but I got this one wrong. Anyway, I have seen X dot whatever less than X dot whatever as well. Anyway, so why is this a terrible, that's one of the reasons it's a terrible thing. Strict weak ordering, right? What is strict weak ordering? It means that your function has to be reflexive. If X is less than Y, Y can't be less than X. They can both be false, that's fine. And think of 3 and 3. 3 is not less than 3, and 3 is not less than 3. But yes, and it's transitive. If 2 is less than 4 and 4 is less than 8, then 2 is less than 8. Right. If your comparison function does not implement a strict weak ordering, bad things will happen. The standard library will not protect you against this. It will, like, if you're lucky, it will just give you subtly wrong answers. Actually, if you're lucky, it will crash very quickly. If you're unlucky, it will give you subtly wrong answers. Anyway, so there's a lot of reasons this is a terrible one, but you get the idea. You can write this as a really simple struct. Most of these are stateless because why would you want a stateful comparison operator? 3 needs to be less than 4 all the time, no matter what the state of your comparison function is. Maybe you want to do some logging, but in general, since it's const, that makes it harder. They return something that can be converted to Boolean. In practice, they just always return bool. So set, map, multi-map, multi-set, all keep their stuff ordered according to this relationship. Smallest first. If you use less, the smallest ones are first. If you use greater, the largest ones are first. This is a cheap way of doing, if you need to pick off like the top 3 and you were scared by priority heap as a young child, and you can do that. You can use a set to this. It's okay. But this is about as complicated as the form of comparators needs to be. Yes?
Excuse me, what if you don't like to create your own struct with the operator or your functor class? What if you wanted to use a lambda to define your code? Because it's going to be, the lambda would be closer to actually the definition of your code or your object than this functor, where you might have it in another class. And if somebody was trying to figure out how it's sorting, they're not going to be able, they have to look at the other class before you go through it.
So the question can be summarized by, and then you can complain about my summary, why don't you use a lambda? Because it's right there in the code. Yeah. And the answer to that is because you can do that, but it's not near as clean as you would like. And the reason for that is because you have to tell the template the type of this. Now, maybe the template argument deduction will help you here. I should try that. But if you have to actually name this, well, lambdas don't really have they have an unpronounceable name. The only way to get it is through decal type. And so you would have to actually take your lambda and put it in a variable and say decal type of that variable. Now, if template argument deduction comes to your rescue, if you don't have your custom allocator that you have to specify or anything like that, if you can just you can go with that, then that will help you a lot. Yeah.
Is the constructor an ODR context? And if not, you can't do that in 17 yet.
Can't do that in 17 yet.
Louis is pushing.
Okay. The question is the constructor run in an ODR context? And I don't know the answer to that. He said that Louis was trying to get this fixed. Template deduction guides may help you here too in 17, but since I haven't implemented those in libc++, I don't know for sure. Shihao.
It works but you still don't want to do that because two lambda standard two different types, therefore you create two different identical.
Ah.
Don't want to do that.
Okay, so he said you don't want to do that because if you have two lambdas, you generate two different types and you end up with containers that you can't really compare, even if they're sorted the same way. So, not yet, okay? We need some more infrastructure in the language to make that work nicely. But I agree that is something to shoot for. Anyway, okay, did that. Here's examples, right? Like the allocator stuff, we had set person. Person, this will not compile unless your person has an operator less than defined on it. This will default construct person less and use that as the comparison. Person less, yes. Some persons are less than others. And in this case, everybody is less than others because I can't type. Anyway, so my set person less. This is really the same as set person less, allocator person v3 person less paren, default constructed person less, default constructed allocator of person less. Okay, and here I'm making a comparison. I'm explicitly passing the comparison function in. Yes. In this case, you don't have to do this because default construction works just fine. But suppose you had some funky constructor for that. Yes, do you have your question?
Yeah, I just was wondering, if you put the new allocator, you'd have a memory leak if you put it in front of personless on the MySet C4, right? Or am I incorrect?
I'm sorry, if you put.
If you put new before curly bracket new person class, that would create an object on the out key that would be a memory leak.
Right. If you said new person less here instead of person less, you'd allocate something on the heap, and you would have a leak because nobody would free it. But more importantly, actually, you would have you get a compile error because it would not, the set doesn't know to say star thing paren. It would just say thing paren and says, I don't know how to paren a pointer. So anyway, I got 5 minutes left and I have like 6 slides left. So let's, so unordered associative containers. Unordered associative containers are just like associative containers, except they're unordered. See, we're done now. So unordered associative containers, the interface looks just like the associative containers, except they have this thing called hash, and they have this thing called pred, and they don't have this thing called comp. And so they're different. They're not the same. They're exactly the same, only different. Now, but most of you, I asked earlier, had been to Matt's talk about implementing hash containers, so you know how hash containers are implemented, right? You hash things into a bucket, and then you use the predicate to find the object you're looking for in the right bucket. Okay? They implement as hash tables, right? The predicate implements equality, not less than. It doesn't try to impose an order on your things. It just says, is this the same as the other? And the hash function and the comparison operator are required to play well together. What the heck does that mean? It means that they have to agree. In particular, because you use the hash to find the right bucket, and then you troll through the bucket to find the right thing. If two things are equal, they have to hash to the same value. If they don't hash to the same value and they're equal, your hash table is going to misbehave. Now, obviously, you can have two things that are not equal hash to the same value. It's called a hash collision. If you think about, suppose you have an unordered set of strings, right? And your hash table, your hash function returns a size t. That's 32 bits or 64 bits. There are way more than that possible strings. You're going to have a collision eventually. Okay, two things that are not equal still may hash to the same value. That's fine. Okay, there are hash talks this week. There were a lot. Some of them were really good. I went to about half of Phil's this morning. Nicholas's talked about hashing as well, but Matt's was great. And that's a very, very fast hash algorithm that I was very impressed by. But anyway, one more slide really. It's important to use a good hash function, okay? You can, in fact, when I talked earlier about bending the containers to your will, you can take an unordered set and bend it to your will, make it into a linked list. Now, most people feel that this is a bug, not this is an idea of something you really don't want to do because you've taken an order 1 lookup and turned it into order n, but hey, maybe that's what you want. So I took, as an example, all the prime numbers less than 100 and dropped them into a hash with 3 different hash functions. This was the type I used. I noticed that here I had int and then this function that takes an int and returns a size t. And I used 3 different hash functions just for testing. I used id hash, which just returns it. I used half hash, which takes the number and divides it by 2. And then I used random hash, which returns a random number chosen by a fair dice roll. So
when you talked about a random number by dice roll, is that that you do one dice roll and choose what number, or is it just a random generated dice?
I rolled a dice once and said, that's a random number, 4. The reference to XKCD, it's a joke, okay? It's not a random hash, it's a constant hash. But anyway, I expected that this one to be okay, and this one to be significantly better, and this one to be terrible. And I was mostly right. This one was okay, this one was okay, and this one was terrible. The reason I expected that this one to be better than the first one is because all the prime numbers, with the exception of 2, are odd. And so I expected half the buckets to be empty because when they all hashed these hashed to itself, right? They never got an even number. But it turns out when I examined it that the number of buckets in the hash table was on the order of 46, 45, something, 47. I think it was a prime number less than 50. And so the fact that it never returned an even number really didn't matter. It still was spread out okay. Both of those, the first 2 behaved about the same. The last one, every single one went into the same bucket. And so I got terrible lookup performance. So the takeaway from this is really, you want to be careful with your hash functions because a good hash function can help you. A bad hash function can absolutely destroy your performance. It can do way more harm than a good hash function can do good. Anyway, and questions, we'll go right through past that, and we'll go on to thank you. And I will happily stay around here and answer questions, but people are done. So yeah, if you've got questions, just come on up.